Okay, we'll continue. There was a couple of things I wanted to point out here that we already saw a couple, right? So the idea here is you create a penalty function which basically describes how you feel, how irritated are you with a residual of a certain value, right? So these are like residuals here, and then this is basically your irritation. And what you're going to do is actually minimize your total irritation, right? By minimizing the sum of these things. And then you can interpret these all sorts of ways. You know, your standard thing would be a quadratic. That's been a tradition for a couple of hundred years. And also has analytical solutions in some simple cases, right? But then we have some others here, like this dead zone linear. And these are interesting because they have like a kink here. And what we observed last time was actually kind of interesting. It was this. It was that when you have a kink here, you find a whole bunch of values right at the kink. Notice that that's also true for the L1 solution as well, right? So the L1 solution says you don't like residuals. In fact, one way to analyze what an L1 penalty function is that for large residuals, it's relatively chill, at least for a convex penalty, right? Because I mean, it's a lot smaller than a quadratic when a residual is large, because a quadratic is large squared, right? Conversely, for small residuals, something like an L1 or something with a sharp point is actually not chill. It gets relatively upset with small residuals, whereas, for example, a square penalty is fine. So, and there's no more to what I'm saying than just this. So don't try to I mean, you can, if you wanted to, people have actually attempted to make this extremely mathematical and so on. It's a bit silly because I think it's actually very interesting to actually just see how this works. Okay. That is actually something, especially this top one, which is the L1 thing. Here you see that a whole bunch of penalties are zero. And in fact, this is a theme you're going to see. You may already have seen it in some statistics and machine learning classes. And basically what people say is that, L1 is a sparsifier, meaning that when you take an L1 norm of something in an optimization problem, it is often the case that at the solution, the argument has a lot of zero entries. That's the case here, okay? And so that's just a common phenomenon, and it's got tons of uses, including a lot of practical uses. We'll get to it in machine learning. There's just tons of them, but it comes up in engineering and has been used actually now for several decades. So, okay. I guess this is we looked at the Huber penalty. That focuses on large residuals and the fact that a Huber penalty is like this Frankenstein penalty that blends together a quadratic for small residuals with basically something that looks like an L1 penalty for large, right? And so you might say that a Huber penalty matches least squares for small residuals, which is to say that it's relatively chill. Not as chill as a dead zone. That's as chill as you can get. That's like, well, okay. But for large residuals, a Huber penalty looks more like an L1 thing, which is for a convex penalty as chill as you can get, right? So, okay. We looked at least norm problems where, basically the same story happens. But now you can kind of guess a lot of stuff. If, for example, X is a sequence of forces that you apply, that you apply to something. Let's say AX equals B says, make me a trajectory of forces to put every 20 milliseconds on this rigid body to move it from this position to that position, right? Let's just say that's what X is, right? If I use an L1 norm here, I want someone to guess, which is, by the way, a kind of a first order approximation of fuel use, at least for rockets. So somebody want to make a guess as to what it's going to look like. What is X going to be? Based on what we were just talking about. It's going to be sparse. Yeah. And by the way, if you go and watch videos of satellites maneuvering or rockets maneuvering, that's exactly what you'll see. if you watch, because you'll actually see puffs come out of the thrusters, and there's little bursts, and you'll see like, 1, 2, 3, and then just nothing. And then some other thruster, you'll get like 2 bursts out of it or something like that. So that's exactly right, they're sparse. Everybody got this? So it's a theme. Don't worry, you're going to see it basically from now on. And it's used in a whole lot of other applications, not just, well, that's one. So anyway, okay, we'll get to that. Okay. We talked about regularized approximation last time as basically a bi-criterion problem where you have 2 criteria. And of course you could extend it and have 3 and things like that. And I think we looked at an example of that, not this one, but optimal input design. We looked at this last time, and this is sort of very typical. This is a pure quadratic problem, so it's not that, it's very simple. You don't need the material of this class to solve this problem. But it looks something like this, right? You're designing an input, which is an input to some system which is given by a convolution, or in dialect, I would say it's a linear time invariant system. That would be like EE and maybe mechanical engineering dialect for what this is, right? So the output is the input convolved with something. I guess in fancy language you would say it's the convolution kernel. That would be something that everyone would understand. But if you're exclusively with people who speak this EEME dialect, you would say something like H is the impulse response, right? So I'm just mentioning that different groups have different names for these things, right? Okay, so here we have like 3 objectives, right? I mean, the first one is we want to track some desired trajectory. We want the input small. I mean, roughly we're making it L2 norm small squared. And we want the input variation to be small. So we want the difference between U, T plus 1, and UT to be relatively small. And so what we'll do is we will minimize a weighted sum of them. These are positive weights, the delta and the eta, that weight the different things, right? And then the way, in fact, people in control and other areas talk about this is they would say that the delta and the eta are knobs, design knobs, that allows you to shape, to make you look like what you want it to look like. Everybody got that? Right. So I guess in machine learning, you'd call them hyperparameters, which are things you wiggle to make, to change your model, to make it less sensitive to something or something like that. Everybody got that? Unlike in machine learning, where you actually have rather good ways to defend choices of delta and eta, in a ton of applications you don't, right? So, I mean, you do kind of, right? So, in control, you'd do something like pick some values and say, ooh, that's nice, saves a lot of fuel, but the ride is too rough, right? And then you would wiggle these things, multiply them, one or two of them by a factor of 2, divide one by a factor of 2, rerun it, and you'd say, okay, we're only using about 5%, we only lost a few percent in fuel efficiency, but it's a lot smoother ride, or something like that. It would be things like this, right? So, okay. And we looked actually at some examples of how that works. And the example actually shows what the whole idea here is. And it's identical to the idea, by the way, in regularization and machine learning, which we'll talk about later. It's identical. And what it is based on is you can actually sometimes get away with not a huge loss in your primary objective, while at the same time actually getting a substantial reduction in your secondary objectives, right? So this is A, a lot smoother than that, and also B, a lot smaller, right? I mean, if this is not good enough tracking error, this versus that, then this is all theoretical, right? But if you're saying like, yo, that's fine, that's all I wanted this thing to do, right? And I think I couldn't remember the name in control or mechanical engineering for this. It's called a doublet. Is that, someone told me anyway. It's something like a doublet motion or something like that. That's what it is when something goes like this. It goes over here, over there, and then back. So, okay. All right, does this make sense? And now I'm going to ask you a question. What would happen if I change this to the sum of the absolute values? You just guess. I mean, 3 lines of Python and you would know, but if someone could just make a guess. What do you think would happen? What?
Be sparse.
Yeah, well, I don't think U is sparse at all. Here, let's go look at U, sorry. If here's you. Well, that's not true. I shouldn't have spoke, right? Here, it does look like it doesn't do anything for 40 steps. It would be sparser, right? What if I changed this to be the sum of the absolute values? What would you get? I mean, you're just guessing here, so. What's that?
Sparse derivative?
Sparse derivative. It's not a derivative, it's a first difference. Yes, sparse first difference. What does it mean if something has, if a time series has a sparse first difference? What does that mean? It's what?
Smoother.
I mean, it's what?
More smooth.
I can't hear.
More smooth?
More smooth. I don't think that's very smooth, no. I mean, it's smooth in a certain sense, right? In the sense that the L1 norm of the first difference is small. I don't know, yeah. Piecewise what?
Kind of constant, and when it changes, it's constant.
It's piecewise constant, right? If I give you a time series and I tell you that the first differences are sparse, then it means that most of the time it's 0, and that means most of the time the value is equal to the previous value. So it would encourage piecewise constant inputs, right? So make sense? Yeah. So that's actually used in like chemical engineering plants when they're planning out changes to inputs and things like that. They actually put a term that looks like this with absolute values, and they even have some great name for that. Like I think what happens then is you get things that says you're going to run 3.5 hours, and then you're going to increase the feed rate to this, right? And then 3 hours after that, you're going to turn up the power to this heater or something like that. And they call those deltas, which is, I mean, it's just dialect, but it's kind of cool that's, and it's done exactly by solving actually quadratic programs. Actually, it looks exactly like that, but with an absolute value here. Okay, so, and the whole idea here should be kind of obvious, right? You can design these penalty terms and objective terms and things like that to get something that you want, right? Like some kind of sparsity or something like that. Okay. Next up is another like very simple problem. It's called signal reconstruction. It didn't stop people from writing 1,000 papers on it, but still, here it is. And it goes like this. So I give you a corrupted signal, and then what you want to do is form you want to form an approximation of it, or an uncorrupted, or cleaned signal, or a reconstructed signal. We're going to call that x hat. That's our variable. X corrupted is given, right? So that would be something like that. And then what you're also given is you're given phi is something like it's a regularization function or a smoothing objective. So it basically says that it says that the larger phi is, the less plausible x hat is as what you're trying to reconstruct, right? So simple things would be things like a quadratic smoother. This would be the one we just talked about. It's an L1 smoother. You could take the third difference and take the L1 difference. You could put a dead zone penalty on the second difference. I mean, there's just a lot of stuff you could do with this. Okay, so this is sort of the idea. Okay. Now, by the way, okay, so let's just take a look at how this works. So here's just a kind of a classic example for how you do signal reconstruction. Like, so here's an original signal, and you can see it's like smooth or something like that. And now here we add some noise to it, and it looks like that, right? And now we simply do, this is with quadratic smoothing, which, by the way, turns out to be linear, and it turns out to be exactly classical smoothing and whatever, all the stuff, well, in EE you would learn and stuff like that. That's what it is. So that's what that is. And is basically the smoother is then, I'll go into dialect, a low pass filter is what people would say, okay? So, and someone would say, what are you doing? And you say, I'm filtering out the high frequency noise here to estimate the signal, which has lots of low frequency content, okay? So that's quasi-dialect for saying this thing is smooth and the noise added to it is much rougher, okay? I mean, you could say that in other dialects too, right? Certainly in time series dialect, you would be able to say something like that. I don't exactly speak that dialect, so I'm not going to even attempt, but you could. Okay, and then here's some examples, right? So you have a trade-off where you're trading off two things, like how far do you deviate from what was given to you, That's this term. And the second term is how small is this quadratic, or how big is this quadratic, or in this case quadratic, smoothing cost. And you can see, this is with this thing is relatively high here, this one, the quadratic component. And this is something like, you might guess, I guess just by eyeball, you might say that's not enough smoothing, which means you should, depends which one you're putting the weight on. Probably you're putting the weight on this, and it says you should probably decrease the weight on the smoothing regularizer. Then you might get something like this. And then you might say over here, well, that's already too smoothed, or something like that, right? So here, by the way, you can use an obvious method to actually, in a very principled way, select the amount of smoothing. You just do cross-validation here, right? So I think a lot of people who do this don't do that, which I find bizarre, but nevertheless, because it's in like your first class on statistics and machine learning, nevertheless you could. And you do that by doing the following. What you do to do that, I'll just explain it, is over here in this one, you take the one that you're given, x corrupted, and you extend this formulation to allow it to have NAs in it. So unknown measurements. Like I didn't get a measurement for index 37, 52, 53, 62, 70, anyway, you do that. And it's actually extremely simple if you make this a sum of squares over those. But the x hat is going to be a full one. It doesn't have any NAs in it, if you're following me. NA meaning not a number, right? Or NaN. I think that would be the other way to say it, right? So, or question mark or whatever, or missing data, right? So then you do this. Now, once you extend this, which is unbelievably simple to handle missing data, now you can do cross-validation. And you do that by saying, thanks for your data, 10% is missing. You randomly yank out another 10% of the data, which you knew but isn't missing, and you pretend it's missing. Now you do signal reconstruction, and you try this thing, and someone at the next desk says, oh, you should try Huber, whatever. Try Huber on the third difference. And you're like, okay, dude. And you try these things. Every time you do that, you can make a prediction, which is x hat, of the values that you actually observed, but pretended you didn't. Everybody see that? And then we can say, thanks for your suggesting of using a Huber penalty on the third difference. Just for the record, it did a lot worse than mine. Okay, so everyone, if you follow that, that's fine. And if you didn't, it's probably okay. Certainly not part of the class, this class. Okay. Now, when your penalty is an L1 norm on the first difference, that's actually got a name. And this is like just completely standard math. It's the total variation, right? So it's actually, well, literally it's in continuous time, it's like the integral of the absolute value of the derivative or something like that, right? And so this is the analog of that. And as we actually reasoned earlier, when you have a penalty, which is like an L1 norm on a difference, you should be expecting the solution to have a difference which is sparse, okay? Which corresponds to a piecewise constant approximation, right? And so here's an example here where here's this original thing, right? And here's the corrupted one. And I'll come back and describe how people in some dialects would describe this. But the point is that's it. Then, now we're going to do L1. Okay. Oh, no, sorry. This is quadratic, right? So in quadratic, you see you do a little bit of smoothing. And good news is like the noise has gone way down. Bad news, you can't really see it here, but that what was actually a transition in one period up here, these sharp things, are now smooth and they go down over 10, 20 periods. That's over here. When I put this amount on it, good news, this noise is attenuated more, but now you can see it's really quite smoothed, right? And then this is like, very smooth, right? So if you wanted to preserve these shifts, right, then you would use, instead of a quadratic smoother, you would use like an L1 smoother, okay? And this sort of makes sense. Oh, I was going to say, like, if you know about audio, this is just applying a low-pass filter, and what you're losing are, for example, the attack of a drum beat, right? And it would just, good news, the noise would be attenuated. Bad news, the drums are muffled. I mean, that was rough, but actually correct, right? What I just said. Okay, so now we do total variation smoothing. So total variation smoothing goes like this. This is maybe not quite enough. This might be about right. But the cool part is, if you take a look at it, it actually has preserved these sharp shocks. Sorry, that's from econometrics, right? So there's a lot. This comes up in lots and lots of fields, all with different dialects and names for everything, right? So, and then this one is sort of interesting. You might say that's a little bit over-regularized, and what you can see here is it's going towards what we guessed was going to happen, right? That you're going to get something that's piecewise constant, right? So, and it would look like this. Okay, everybody got this? And so there's no mystery here. It just it just follows from knowing about what happens with L1 norms and things like that. So let's see. I should probably make some other. So you get the same thing. You get total variation denoising, for example, in images. That's actually super interesting. It's actually not a sum of you can do a sum of absolute values. You can take an image, right? Let's say represented by a matrix, right? And you could do something like this, right? You could have ij plus 1, and then you would have xij minus xi minus 1, or right, and j, right? And so you could take the L1 norm of that and then sum it over all pixels in your image, right? Everybody, right? This is sort of like this is a very crude idea of the space gradient in the image, right? Okay, so it turns out a very good thing to do there. If you actually take the L1 norm of this, you actually end up with artifacts that are aligned with the axes. But if you just simply do this, this is a generalization of an absolute value. If you take this objective here, let me draw that a little bit better, right? By the way, this is not squared. It is not squared. It's just the sum of the norms. Everybody got that? That's called total variation. That's a total variation penalty for images. That works actually really well, like quite well. I mean, if you want to get into fancier ones, you can. But this is as a first cut, this is actually really quite good. And what happens there is it preserves. It's going to preserve sharp boundaries. Obviously there's boundaries. If I'm looking over there, some pixels are the podium and some is the chair behind it. And there's a sharp boundary. And if I were to do this, smoothing with this, I'm just doing a linear smoothing with a kernel that goes down like that, and it's going to blur things. Everybody follow? I mean, you don't have to follow this, but if you know some of the stuff I'm talking about, that's great. So this is total variation. That people refer to that as total variation image denoising. Have people seen this? Who's seen this before? Somewhere. Okay, cool. In where? Like in what kind of?
Pressure jumps across shock waves.
Mm-hmm. Mm-hmm. Yeah. So
we have a similar.
Yeah. So this preserves. What happens if I use excessive regularization of this on an image? So I have a black and white image. I give it to you, and you say, "I just learned about total variation, whatever denoising," and you use too much of this regularization. What do you get? Just guess. I think everyone can guess.
Blur.
What?
Blur.
Same color?
Ooh. Yeah, okay, sorry, yes. Not a blur. No, I don't think you. So, if you, by the way, you add too much like L1 regularization, what's the limit of that? What happens when I add like an enormous amount? It's 0, which is indeed very sparse, right? You have to admit that, right? Okay, so yes, if it was way too high, it would say, here's your new image, and the entire thing is just some grayscale value, right? Which is kind of the app. Okay, everybody got that? Okay, let's crank it down to something reasonable, right? And what do you think happens? I mean, it's something like this phenomenon here, right? What do you think? But in an image, what do you think what would be the phenomenon in an image? What's that? Yeah, you'd get edges and regions with a constant grayscale value. Yeah. So actually what you'd end up getting is like cartoonish looking things, right? Because you take an image with 8-bit or whatever it is, 8-bit stuff, and then you end up with 3 different values, and you get regions. So, okay. These are just sort of examples to give you the idea of how these things are done. But okay. Next topic, which is something we're going to talk about also in other contexts, like a statistical context, is the idea of robust approximation. So, robustness is this thing. I think we've talked about it before. It's a universal thing. If you do anything with math at all, then it's something you need to be aware of, right? Your model is not what you think it is. Might be really accurate if we're talking electromagnetics or photonics or E&M or these or Newtonian mechanics. It's pretty accurate, thank you. But in other cases, it's not at all, right? That would be in areas like machine learning or, for that matter, finance, right? Right. Your model is just a fantasy, and it's not what's actually happening, right? Newtonian mechanics, I'd say it's kind of is what's happening, right? E&M, your model is actually kind of what's happening. So, although even there's questions, right? You might not know stuff and things like that. Okay, so here it is. We want to have an approximation problem. We want to minimize, norm AX minus B. But we're going to actually address the idea that we don't know A. So, you don't know A. By the way, let's talk about how do most people in practice handle uncertainty? What's the most common method for handling uncertainty? It's not fancy. Well, how do most people handle uncertainty? Look, right now as we're speaking, people are doing supply. They're working out supply. I guarantee you, Amazon is working out supply chains, right? They're deciding stuff that's going to go to the various warehouses and land at fulfillment centers in the Bay Area. Obviously, they don't know. So how do they handle the uncertainty? Mostly.
They have mean and some variance, assume a probability distribution.
That's a good question. So the question is they have a mean and a variance for A way. Turns out that's not true. Okay, it's even dumber. What's the simplest way to handle uncertainty?
They simulate multiple scenarios.
I mean, you guys are too. You really think things are that sophisticated? What do you do?
Buffer capacity, like a safety stock, I think.
Yeah. I can't believe this. It's time for you to know something about the real world, which is horrifying. What is the simplest way to handle uncertainty? What?
They guess.
They guess. Okay. Now, what is that? They're getting close. What does that mean? Guess.
Educated guess.
Educated guess. Okay, sorry. So, but in particular, here's what they do. They just ignore it. You just ignore it, right? I mean, that I guarantee you that's how 99% of actual uncertainty in practice is handled. You're like, this is the demand we think for these products over the next hours and days, or something like that. And you're like, you just say, cool, thanks. And then you solve some big convex problem to figure out what to do. Everybody, that's actually kind of what happens, right? I mean, they're, not always. You just ignore it. By the way, ignoring it and then just go ahead and implementing it is a very bad idea. So the least you could do, and now I'll take some of these suggestions, is what? The least you can do if you ignore it, if someone says, look, here's my data, and then they say, oh, the data's really, it changes quite, it can be not what I'm saying, right? And you say, yeah, no problem, thanks. If they give you anyway, they give you 50 different values for possible values for A, you just take the average or something like that and then go with it, right? But what should you do then? What would you do at that point? Well, the least you, yeah? You can you simulate it with that. So that would be probably the ones that I don't think are criminal, that would be an approach that's not criminal, right? If someone comes to you and says, oh, I've generated samples from what I think A is. And you go, cool, thank you, right? Then the first thing you do is you form the average of A or the median or something like that. Use it in this thing. You get an X, and then you simulate this thing across all the individual samples. Everybody following that? And by the way, if it's pretty tight, you just say done, right? So that's the least. Okay, so there are methods for handling uncertainty. Like I said, anyone who does anything in practice anywhere is going to have regularization. They may not call it regularization. They might call it, robustness. That would be one name for it. It's got lots of names, but you can't make anything practical work without addressing this uncertainty somehow. Actually, all of regularization in machine learning statistics, all of it is nothing but addressing uncertainty like this in data and stuff like that. Okay, so let's take. So we'll look at a couple. Now we're going to look at fancy methods for doing this. Well, there's different approaches. I think we saw these in some very early examples. But so one is stochastic, right? So you say A comes from a distribution. It comes from a named distribution, or you could have, who knows? It could actually be something from which you can sample A's if you have a fancy model for it, right? That would be something. Another, actually probably better defensible, is you estimate A. A is itself. There's a whole department that's estimating A. By A, I just mean the model, right? Or people say the forward model. The whole department doing it. And they could do things like what you do is you say to them, don't give me one model. Give me 50 plausible models. And what they would then do is they would say, cool, if you're going with one, here's the A we think you should use. But here's 50 others that are consistent with everything we know and we have seen. Everybody understand what I just said? So that's like ideal. That's like, okay, thank you, right? Or you could say, here's 1,000, because I have that department that does the modeling says, I actually have a generative model. I can generate you how many A's you want, right? I'll just sample from that distribution. Everybody following this, right? So that's stochastic, right? And then you might do something like actually minimize the expected value. Now that's a convex problem. I mean, because expectation preserves minimization, expectation preserves convexity, right? So, okay. At the other end, people do worst case, right? And this would be something like, look, I don't even believe it. It's not generated from probability distribution, which is true of almost everything, like almost nothing is, right? So it's ridiculous. It's not from a probability distribution. You'd say, but my experience says I think that the entries in this matrix are correct plus minus 3%. I mean, it could be a lot more sophisticated than that, right? You could say, well, the diagonal entries, I know this well. These things, oh, that entry, I barely know the sign. Everybody following us? It'd be things like that. So you could make up something like that. And then you could say, well, which A is it? And you'd say, any A that satisfies the constraints that I just described to you is plausible, right? And then by the way, they have huge philosophical fights, which is kind of hilarious, right? So the worst case people say like, oh my God, it's so unsophisticated to assume a distribution, right? And they're like, that's ridiculous because it's not a probability distribution, blah, 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 and stuff like that. And then, I don't know, the stochastic people, it'd be like a fight between Bayesians and frequentists or whatever. Anyway, so, and then the stochastic one would say something like, oh, the worst case is way too conservative. And you're like, none of this makes any sense, by the way. They're both, but they're much closer than they think. And actually, a lot of times it's embarrassing because they have this huge philosophical argument, and then it turns out you work out the math of what they're doing, and they're doing exactly the same thing, right? Where one person has a knob that says how big their uncertainty set is, and the other has a knob that's basically like variance or something like that, right? So it turns out they're doing kind of the same thing. Oh, and there are hybrids of these, right? There's robust stochastic. And then you'd say, well, here's my uncertain parameter, right? It's from a probability distribution. And you go, cool, do you mind giving me the parameters? And you go, aha, no. I give you a set of parameters, right? And then they would claim that this gives you like the advantages of both of these methods or something. Anyway, this is just to give you the big picture of uncertainty modeling and things like that. Okay, all right. Okay, so here's just a baby example to see what the idea is. So here, I mean, it's a matrix, right? I don't know how big it is. It doesn't really matter, but it's a matrix, right? And what we're going to do is we're going to have extremely explicit uncertainty. It's extremely dumb. There's a line segment in matrix space. I mean, that's kind of silly, right? Because it's a more common model would be these entries are all plus minus 1% and things like that, right? So, okay. But this is just to make the example so we can work out exactly what happens. So the A that you get is parameterized by U, and we'll okay, here it is. And so this is what people would normally do. They would say, what does my matrix looks like? It looks like that. U is centered around 0, and they'd say, cool, my A matrix is A0, period, right? And that would give you this curve here. And what this is showing you is here, this is what happens when A is A0. This is what happens as you change A. And you can see, there's going to be these other methods. They're not as good as this one. This one it has the absolute minimum value here. And you can see that as, your error is like, I don't know what this is, 3. And then by the time this gets to -1, it's double, it's 6, right? And so you might say, well, this is too sensitive, right? Then you might look at the stochastic one. So here's this is the stochastic one. And what we do there is we minimize basically the integral of this over this range. And that gives you this one here. And what you can see here is so here's how people would say this. You have given up nominal performance, right? So you gave up nominal performance. And what you got was something that was much less sensitive to the variations. Everybody see this? And I mean, that's kind of the story you want. That is exactly the story that's what you want to happen, right? And then the worst case one, again, that's not hard to solve. And it turns out for the worst case one here, you can see you gave up some performance here, but you can see that it's incredibly robust, right? So so this picture plays out, and obviously in much more sophisticated settings, but this is the story that you want to have when you have a method that addresses robustness, right? So, or uncertainty. So does this, all this make sense? Yeah. So I can tell you a little trick. You want to hear a C? Yeah, but this is unofficial, so you can't tell people where you learn this. Okay, so it turns out, here, as a street fighting matter, it turns out that all you need is like just literally a shockingly small number of samples of A, and then you do something like a minimax or something like that, which would be something like this, a very crude approximation of this worst case thing, does the trick, right? So for example, if you say, design me a trajectory for, I don't know, this drone or something goes from here to there, right? And you go like, okay, can I have the model? And they go, yeah, sure. And they go, well, what are these parameters? And you go, we don't know. They can vary, right? That's the, because it depends on the payload and blah, blah, blah. And by the way, even if I tell you the payload, I might not know it within, plus or minus 5% or something like that. So there, it turns out an extremely good thing to do is you just ask whoever is coming up with the model, you'd say, give me 10 models, right? And you say, here are the rules. They have to be plausible, right? They can't be, they can't give you some crazy thing. You'd say every one of these, you would have to defend as a plausible model, that it's consistent with what you know about the problem and the past data. Everybody see what I'm saying? And they could do that all sorts of, so you might do it this way. You'd say, not a problem. I'll fit a model on Monday data, Tuesday data, Wednesday data, and Thursday data. Done. Now you have 7 different models. If they're wildly different, something's weird. If they're all the same as doubles, what do you think has happened? What would you do if you asked someone to make a model of something and they go, cool, I made one for Monday, Tuesday, Wednesday, Thursday. And you go, God, thanks so much. And then they're kind of like equal as doubles. It's not a convex optimization question here. What would you do?
Variation is not dependent on the days, so it's
Nah, that's not. No. Yeah, what, really? You think out of the 8th significant figure, it doesn't? No. It's fraud. That's what it is. They just lied. They just gave you 7 copies of a single model. So, the least they should do is cover their tracks and add a little bit of random into the model. I mean, come on, right? So if you're in this situation and some crazy person comes to you and says, you get 10 models, yeah. So just for fun, that'd be one extreme. So fraud is one approach to generating a set of models. Let's do a principled one in statistics. We're jumping ahead, but I don't mind doing it. How would you make a principled one in statistics? So you're fitting a model, let's say maximum likelihood. Sorry, I'm getting ahead, but you can just pretend. If you don't know what I'm talking about, that's fine too. Someone tell me a good way to honor a request for 10 plausible models. We'll do maximum likelihood here. Someone tell me how to get 10 models. That's what I want to know. And don't pretend there's no one in statistics here, because I know there's a lot of people in statistics here. So don't, yeah, go ahead. Somebody make a suggestion? You were going to make what?
Do you bootstrap just like 10?
That would be fun. Bootstrap would be fine. Here's a simple way that is convex optimization. You would do this. Certainly, you would find the maximum likelihood estimate. And you'd send that parameter and say, if you have to go with one, take this one, right? Okay. But then what you would do is you'd find the maximum likelihood. I will draw the likelihood function right now. Sorry, I'm getting ahead of myself, but it's just fun. So here's the likelihood function. Here's the maximum likelihood point, right? What you'd do is you'd record what the maximum likelihood is, drop to a likelihood level that is slightly less than the maximum likelihood, which is completely defensible statistically. And then what you would do is you would find points in here, right? Like that. I mean, I guess depends. If it's all smooth, this would be like from you'd sample from the Fisher, the Fisher information, the ellipsoid defined by it. Okay, sorry, that was weird. I just couldn't help myself. But did everybody get that? And then someone said, "What have you given me?" And you'd say, "I gave you 10 models." And you go, well, you say the first one is actually the maximum likelihood. If you're going to go with one, I'd go with that if I were you. And you go, what are the other 10 or 100? And you would say, oh, those are models whose parameters are almost maximum likelihood. Everybody got that? Okay. And then you'd say, thank you. And then you'd come over here and you'd do something with, and then you'd, put these in as a maximum or something like that, or an average. It wouldn't matter. Oh, sorry. And I was going to tell you the secret on this. The secret is by simply admitting and acknowledging that there is uncertainty gets you like 90% of the way there. Then you can do all these fancy things later and, blah, blah, blah. But the point is just doing 10 is good enough. So now you know a secret, right? So if I go to my forecasting group and I tell you, here's the demand for this product over the next week, hour by hour. And you go, okay. You go, are you certain? And they're like, no. And then they say, please generate me 10 such trajectories or 100. I don't care, right? Then this tells you it's fine. And you say, but the rule is they have to be defensible. They can't be like weird things, right? Every single one would have to pass as a model, right? So that's what you would do. Okay, so sorry, that was just a weird aside on all these things. Okay, but this is the picture. So you can actually do things like stochastic robust least squares. And I'll go through this because it actually is very cool and it tells you about what regularization really is. So here it is. So we're going to do least squares. Here we are. So it's 1805 now and we're doing least squares. And so our model is going to be stochastic. We're going to say, well, no, I don't know A is A bar. That's kind of like a nominal value of A plus U. Use a random matrix, zero mean. And let's say that the expected value of each entry is U is P, right? So if P were like little sigma squared I, it says all the entries are all completely independent and they're all perturbed by an N0 sigma squared, little sigma squared value. Everybody independently. Completely reasonable. By the way, if someone gives you a matrix and you say how accurate are the entries and they can't say, find someone else to work with. Because in any practice, if you can't say something like, oh, those are pretty good, like third significant digit is actually like probably right, that's one thing. Or if they say the second digit is meaningless. So if they can't say anything, then just find someone else to work with because this is not someone who knows what they're doing. Everybody got that? Okay. All right, so this is one of those cases where you can just analytically work this out. I mean, you just expand this and you get something really, really cool. It turns out you should solve this problem here. It's super interesting. It's super simple, right? And actually now, let's just take P equals, delta I, right? So delta would be little sigma squared I, right? Then it's very cool. You end up with this and you go, oh, that's taken off regularization. So you can turn this around and someone says, what are you doing? And you go, well, I'm doing regularized least squares. Like I'm doing ridge regression, you would say here, or you'd say taken off regularization or something like that, right? And they'd say, Why? And one thing you could say is, yeah, because I don't know A, right? And I think we already talked about the fact that this makes sense, because the thing that happened, AX is sort of the result, right? If A is uncertain and X is big, you get a lot of uncertainty in the result. If X is small, like if it's 0, doesn't matter what A is. Everybody following this? So this all sort of makes sense, but it's very cool. So it means that, well, now you know what taken off regularization is, or ridge regression is, right? It's basically saying that all of your data, I guess let's say in a regression context, you're basically saying, thank you for all your features, your feature matrix, because that's what A is, right? Basically it says, I don't trust all these features are plus minus, 0.01. They're disturbed by independent Gaussians. Everybody follow me this? So that's what this, and then it says that suggests a taken off parameter, right? So that makes sense? I mean, I think it's kind of cool, right? I'm not going to go into the details of this because it's actually like quite complicated, but you can actually do a weird thing with, you can actually work out the case where A is this is an ellipsoid in matrix space. That's what that is, right? This would be the analog of the previous one. In the previous one, I made I didn't say what the distribution was, but I told you it's first and second moments, right? But I didn't say it was Gaussian or anything, but anyway. So here, this would be like this would be the ellipsoid. And you say any matrix in this ellipsoid is a plausible model. You can actually solve, I'm not going to go through it, but it's actually, these are things that, let's say Lagrange would not have known. Let's just put it that way. Probably could have explained it to him pretty quickly, to be honest, but nevertheless, well, okay, they'd have some questions like how on earth do you solve that problem? But we'd have an answer for that too, right? So, okay, I'm not going to look at it. We won't go into the details because it's quite complicated, but I'll just show you the results, which are really very cool. Oh, and this is, by the way, the kind of thing you'd expect to have, right? Let me explain what we're doing. So here's what we're doing is this is now, I have a disk in matrix space. I mean, it's a baby example, right? But I have a disk. That's what this is if you think about it, right? It's two-dimensional. It goes off in these two directions, A1 and A2. I have a disk. And actually, I put a uniform distribution on the disk, on the unit, this unit disk, right? That's what actually happens. So this one is cool. This is X least squares. That just says that's the traditional method of handling uncertainty, which is ignore it. And I just plug in the mean and I calculate X, right? And then you get this distribution like this, which you should do anyway, just to check. And that's a message to you that you probably shouldn't, that you need to be a little bit more sophisticated than just ignoring uncertainty, okay? So, and let me just check on a few things here. Let's describe. How would you describe in words these events? What would you say?
Worst case scenario?
Yeah, you just say, look, this is bad. These are perturbations to A where my choice of X gave me a really big residual, right? So these are kind of, this is bad luck or something. Oh, by the way, how do you describe these?
Best case.
Yeah. What would you call it?
Good luck.
Yeah. Good. Yeah. How about dumb luck? Right, because you're using a dumb method, right? And sure enough, 5% of the time, the perturbation of A is in a way that actually helped you, right? So this is, I would call this dumb luck, right? Then we look at ticking off here, or ridge regression, if you want to, that's a different dialect for it, right? So if you do ridge regression, you get this, and actually it's really cool to see you see immediately kind of what adding regularization does, right? It tightens the distribution with respect, in this case, it's with respect to a very specific perturbation of the parameters, right? So that's this one. And then when you do the robust least squares, I mean, that's unfair because we told it exactly what the disk was and stuff like that. And you can see you get this beautiful, very tight distribution. So make sense? Yeah, okay, so, this is, and these are all like convex problems and stuff like that. So, okay. All right, so our next topic is a statistical estimation. It's extremely elementary, but we'll talk about it's sort of interesting. So actually, it's one of those things where if you haven't seen this stuff before, you're not going to understand it from what I say. And if you've seen it before, you'll be bored out of your mind or something like that. So I'll probably tell some weird stories, through it anyway, just to make it more interesting. But here we go. So we'll just start with parametric distribution estimation, right? So here's the idea, is that we have a density, and we have an observed value of something. We have a density, but the density is indexed by a parameter. Like, for example, a Gaussian would be indexed by, let's say, its mean and its covariance matrix, let's say, right? Or a Poisson, variable by its rate or something like this, or an exponential variable by its rate or whatever it is, right? So you'd have parameters. And what we'll do is we'll put the parameter as a subscript. So Px of y is going to be the density with parameter values x at the point y, right? So that's called the likelihood function, right? People often work with the log likelihood function. Obviously, maximizing a likelihood and a log likelihood are the same thing. And so you would have something that looks like this. So here, this is an estimator for x, and you're given y, which is an observation. And it's, it kind of makes sense, and you could argue a lot of things about it. And if you take a statistics 101 class, you'll hear a lot about properties of this, right? So, okay, so that's maximum likelihood estimation. So as I said, this is called the log likelihood function. By the way, here what we're doing is we're considering this a function of x, which is the parameter in the distribution, not of y, right? So, and you can add constraints to this. For example, if this is a Gaussian distribution, let's say scalar, with mean mu and standard deviation little sigma, right? Then, little sigma has to be positive. Like, otherwise it makes no sense at all. So you would add that as a constraint, or simply define the likelihood to be 0. If you say, what density do I get what's my likelihood if I guess that the standard deviation is -1? Aside from that being profoundly stupid, you just get 0. And then log of 0 is minus infinity, and that means you did a very bad job of maximizing, right? So, okay. You can add regularization too. So regularized maximum likelihood you could do. So the question is, when is this convex? And it's convex when the log likelihood function is concave, okay? So now you have to be super careful, because up till now we saw the idea of a log concave distribution or density. So a density is log concave if, when you fix x, this thing is concave in y. That's a log concave density, right? This is not that. This is the opposite. This is, how does this vary as a function of when you fix y of x, which is the parameter in the distribution. Everybody got that? Now it's going to turn out that there's lots of cases, like if it's an exponential family, then it's going to turn out they're the same thing. But in general, they're different. So I'm just going slow just to make sure this is all totally clear. Okay, so that's it. So roughly speaking, maximum likelihood is estimation is a convex problem when the log likelihood function is concave, which is not the same as saying that the densities are all log concave. That's a different thing. Okay, so we'll just look at some simple examples here. So here's one. It's a traditional linear measurement model. So I make a bunch of measurements, and they're going to look like yi. So yi is, and my model is going to be that each yi, which is a scalar, is a linear function of x here, plus a noise, which is independent, across different i's, right? So that's what the model is, right? And so actually it's kind of interesting, because someone in like EE or something like that would describe this in a pretty simple way. They would say something like, x is what you really want to measure. AI tells you what your ith measurement is, like, oh, that's a radar snapshot from this position, like that. Or A7 is what I deduced from some GPS thing or something like that, right? And they say, Well, that's how they would describe the problem, right? So, but the statistician would have to describe it this way. They would say that what you observe from your sensor suite actually comes from a distribution. And you go, oh, okay. And then you say, the distribution changes, it's parametrized by this X. Everybody got that? I mean, they're saying the same thing, but I'm just saying this is the language a statistician would use. And then they would say, so your problem is really to estimate which distribution generated the measurements, the 27 measurements you actually got. Everybody following this, right? Whereas I think a normal person would just say something like, that's the model. These are the 27 measurements I got. These are independent. Could you please guess what X is, right? So, I mean, I have lots of friends who are statisticians, so this is fine. So I'll find. Actually, that's how I picked up their dialect. So actually it makes me very nervous when anyway, so which I of course enjoy. So anyway, all right. Okay, so let's see how this works. If Y's, this is these are independent, right? So what you're really saying here is something like, Yi minus Ai transpose X, which is Vi. These are independent, right? So the density is the product of the densities. So the density of the vector of measurements is equal to this thing, right, over here. And you take the log of that and you get this, right? And here, this is, the variable here is X, right? So what's interesting here is this thing is a convex problem, which is to say that the log likelihood is convex. In this case, it coincides exactly with the density being long concave. So this is a case where the two are the same, right? So because actually you see something here. It's right. It's because basically the X, if this thing is log concave, so if it's a log concave density, then that tells you that this is concave in log P is concave in this. Right, but if log concave if P is such that this is a concave function, then this is precomposition with an affine function. And so these are concave functions of X. I don't know if that makes sense. So that's the picture. Okay, so all right, and let's look at some specific examples. Right, so someone says, okay, the noises are Gaussian, and you'd say, well, here's the log likelihood function, and you see it's a constant minus a quadratic, right? But you see immediately is the maximum likelihood solution is the least squares solution, right? So this says if you're doing least squares and you want to make it sound fancy and brush someone off, they'd say, what are you doing? And you go, oh, I'm doing maximum likelihood estimation with a Gaussian distribution, noise distribution, or something like that, right? So everybody got that? Okay. You could have, let's make the noise Laplacian, right? So Laplacian means that it looks like the density looks like this, right? It's here's 0, right? And it goes like this, right? And out here, it's got way, way bigger tails than a Gaussian, right? And for the same, let's say, for the same whatever variance, right? So and what this says is you now take, the log of this, and you end up with this, and you see that's cool. So maximum likelihood estimation with Laplacian noise, right, is basically L1 estimation. By the way, we can actually now figure something out. We can understand robustness now from two completely different things. Earlier today, I was just drawing down, let's compare the square and the quadratic, right? So the square penalty looks like this, right? And then the absolute value looks like that, right? We'd say if you're not doing a statistical interpretation, you would say, well, the difference between least squares and L1 estimation is two, really. One, let's focus on the large residuals, right? You'd say, well, least squares is going to be very sensitive to large residuals. Like it really doesn't like them because it squares them, right? And you'd say, by contrast, L1 is going to be much more chill. Everybody got what I'm saying? And so you'd say, and what does that mean? And you go, well, what it means is that when you do L1 estimation, it's much less sensitive to outliers. That's what it means. So it's a robust estimator, actually, literally in the statistics sense, right? So it's a robust estimator, okay? What's cool is you get the same, you can argue it here. You could say, well, the difference between like L2 fitting and L1 approximation, you say the difference is actually basically this. It's a difference between whether you believe the noise density looks like this or looks like this, right? That's a pretty bad job of it's a horrible Gaussian, but you get the idea, right? So it looks like that. And actually, you pick everything off from this, right? Like you would say, look, if you thought your noises were Laplacian, then the probability of like a 3 sigma event is not insignificant. I mean, you could expect to have a noise which is like 3 times the standard deviation, right? That's the whole point, right? Or 4 times, right? Or something in there. It can happen. Gaussian can't happen. I mean, kinda, you know what I mean, right? It's extremely unlikely, right? So you'd say, so if I were you, your estimation, if it's going to work well, it cannot be sensitive to these large noises. Everybody following this? So that's why. So that explains why L1 estimation would be actually more robust than the other one, right? Because you're basically fitting with the presumption that your noises have fat tails, right? So, oh, and this is actually interesting too. This is not the main point, but if you look up here, it's actually super interesting, right? So if you zoom in on a Gaussian, it's uniform density at the top, right? It just looks, it's uniform, right? And you're saying, well, what that means is like, it means once your residual is smaller than when you zoom in and a Gaussian looks like it's flat, once your residual is in there, like you don't care if it's like 0.01 or minus 0.03, you couldn't care less. They're all equally likely, statistically speaking, they're all reasonable. Everybody see what I'm saying? For a Laplacian noise, that's not the case, right? As a matter of fact, there's a sharp peak, and actually being 0 is actually quite likely. And that explains also why you get weird, the sparsity and stuff like that. But okay, so does this all make sense? And let's do one more just for fun. And you can turn this backwards and forwards. So let's do one more. You tell me, suppose someone says, I'm going to use Huber fitting. That looks like this. It's quadratic up to some threshold, and then it goes linear. Okay? So there's Huber fitting. And someone says, why are you doing that? And you go, well, because it's like, I want to do least squares, but I want to be insensitive to occasional weird large noises, right? Done. That's more than a good enough explanation. But suppose you wanted to defend it statistically. In fact, how would you describe it? How would you say, what is Huber fitting when you're doing it statistically? How do you describe, what is it in terms of maximum likelihood? How do you translate it to that dialect? What's Huber fitting with, what maximum likelihood problem does it correspond to?
Is it like a mix of the two?
It's not a mixture. It's close, right? It's actually pretty close to a mixture, but it's not. It's actually it says, oh, I'm doing maximum likelihood estimation. You go, with what density, noise density? And they would say, well, it's this weird Frankenstein density that looks like this. It looks like this. It's a Gaussian, right? It's actually e to the minus this, right? So it's actually literally exactly a Gaussian, right? Out to some threshold. And then you glue onto it an exponential tail. Everybody got that? Because that's what the exp of the Huber thing is, right? You have to normalize it, but who cares, right? But it looks like that. Everyone agree? And someone said, well, what are you doing? And you go, I'm doing maximum likelihood estimation. And you go, then why aren't you using it? And you say it's pretty much Gaussian, but I'm going to use Huber instead. And they'd say, what does that mean? And you say, well, what it really means is I'm assuming that my noise density, this thing would go way down. I mean, I'd have to adjust things to get the normalization right, but whatever. The density is proportional to this. So what you do is you just take a Gaussian, cut it, and then glue on exponential tails. If you do maximum likelihood estimation, congratulations, you're doing Huber fitting. Everybody got this? Make sense? So it's just lots of ways to understand exactly the same thing, right? What if I did fitting with with a dead zone linear penalty. That's maximum likelihood for what? What's your noise density for that? Yeah, you say, well, my noise is this. It's actually flat. It's a uniform It's a uniform over some interval, and then that's some fraction of the probability, and then I glue on exponential tails. So you'd say actually between plus and minus 0.1, it's just uniform. I mean, you're equally likely to have anything in there in the noise. And you'd say occasionally though you get some big things, and those are these exponential tails you glued on, right? Everybody. So all make sense? So okay. Okay. We'll look at just a couple of others. So logistic regression, which I very much hope many people have seen, but anyway. And it's the same sort of thing, right? You would say, I have I have a random variable, takes value 0, 1, and the probability of being 1 is a logistic of this thing, which is an affine function of some features or explanatory variables that you can see, right? So that's what it would be. And so that is the, and here you would say something like, conditioned on U, you'd say the density, the probability mass function, or just the probability that it's 1, right? It depends on a parameter, which is A and B, right? And if you just take if you take the log of this, you end up with this thing, and it comes down here, and you can see immediately that this is going to be concave, right? Because this is, that's affine, right? And then this is log some x, because this is exp of 0, right? So this is log some exp, right? I think that's the logistic loss, right? And with a minus sign, it becomes concave, and affine is concave, right? So that's a mac. I mean, I'm sure people have seen this, right? So that's the idea. So that's logistic modeling. And then, this would just be like a little baby example, right? So the example is here I have one explanatory variable U, right? Which might be, age or, I don't know, I'm just making this up, right? Age, and this is the probability that when you're admitted for something to the ER, you survive. I mean, I'm just making this up, but that would be it, right? So, it looks like young people don't do very well and older people do pretty well. Maybe this is maybe that's the probability that you don't survive. How about that? Then this makes sense. Then it has the right flavor, right? So, okay. And so, these dots are your sample, the data you have, right? You'd say, here's someone who was 63, didn't survive. Here's someone who was 27, did survive, or something like that, that kind of thing. That's the data. And, your eyeball would look at it and say, look, the probability of being 1 is higher when U is large. But, there's things that are not obvious. Like, like how about there's someone like really old and for whatever reason, they survived, right? Or something like that. I'm just making this up. Okay. And if you fit, now that's just a convex problem to fit it, and you would fit it, and you'd end up with this curve here, right? So it looks like that, this curve here. It kind of makes sense. Let me ask you a couple of questions about this. What if the data actually looked like this? What if the data looked like this? Here's U. And suppose it looked like here's 1 and here's 0. And suppose there's a whole bunch of points along here, right? And then there's a whole bunch of points along here. So a couple of questions. What does it mean? Tell me about the maximum likelihood problem, and let's just talk about that. So what does it mean? This means, look, everyone less than 32 survived. No one above that age survived. Okay? So you tell me, what does it mean? I mean, there's so many ways to say this in different dialects. It's, yeah.
Linearly separable.
Yeah, you would say that the data are linearly separable, right? Okay. What about the logistic? The log likelihood. Suppose I ask you to maximize the log likelihood here. Again, you can just guess, or you might know, but what do you think is going to happen? Any guesses? How should I draw your actual? I'll draw the logistic map corresponding to the maximum likelihood. What's it going to look like? Yeah. Okay. I'll take your. It's going to look like this, right? It's going to have a super sharp like that, right? Okay. How sharp is this going to be? Infinitely sharp, because the less sharp you make this, you start dropping the probability here. But you know everyone over age 33 survived, so you're losing log likelihood, right? And the other thing too is if you make this less than infinite slope here, then you're shortchanging the predictions here, right? So in this case, this is precisely the case when the log likelihood is unbounded above, right? So this is extremely common in models, right? If the log likelihood is unbounded above, it means they're separable and stuff like that, right? So, of course, this is fixed by regression and things like that. Sorry, by adding regularization, right? So that's fine. Okay. All right. Our last topic is just sort of a whirlwind of topics. There's more in the book, which we'd expect you to be reading, but. And the last one is just on kind of basic hypothesis testing, right? So, and the setting here, it's super simple setting. It just says, I have a random variable, and for fun, I'm just going to make it with values in 1 to n, right? And it was generated from one of two different distributions, and you have to guess which one it was generated from. Did it come from P? Did it come from Q? That's your question, right? I mean, it's the basic question here, right? And the way that's going to work is an outcome is going to happen. Like I'm going to say, okay, I observe 7, right? And then from that, you have to guess, like, was it from distribution P or Q? You could almost guess, or from a course, you would certainly know what the optimal guess is, right? I mean, it'd be very weird if P7 was like 0.8 or something, and Q7 was 0.05. And I said, 7 is what occurred. Which one do you think it came from? And you go, oh, Q. It's just, I mean, if you think carefully about it, that's weird. I mean, unless you know something secretly behind it, you must know something, right? And you go, whoa, it's much more likely with the first model than the second. And you go, yeah, but I've been doing this for 20 years. I got a good feel for these things. So go with Q. I mean, anyway, I'm just saying, you could even guess what it is, but we'll just work out what it is. Okay. So what we're going to do is we're going to look at a randomized detector, and a randomized detector is like a 2 by n matrix. It's a very weird thing. It looks like this, right? So it's a 2 by n matrix. It looks like 0.8, 0.2, 1, 0, 0, 1. That's good. And 0.3 and 0.7, right? And let's say this is P and Q, right? And this is the outcome. This is 1, and that's n, okay? So the idea here is, this is my detector. It's a policy, and what it does is it says that if the outcome is 2, I will simply say it came from P, period. Everybody following this? If the outcome is 3, I'll say it came from Q. If the outcome is 1, I will then do something very weird. I'll flip a coin with probability 0.8, and if it comes up heads, I'll say it's P, otherwise I'll say it's Q, right? Everybody got that? By the way, we're going to see examples where you need a randomized detector, right? Oh, a deterministic detector is when all the numbers in that matrix are 0 or 1. And then it's just a partition of the outcomes, which are 1 to n, into the ones where you guess it's P and the ones where you guess it's Q. Yeah?
Isn't P a distribution and Q is a distribution?
Yeah, those are n numbers that are non-negative and add up to 1. Yeah.
But like here they don't add up to 1, right?
This is a detector matrix. This is not a probability distribution. This is not a probability distribution at all. Yeah. So P and Q do. Those things, of course, right? The sum of the PIs is 1, sum of the QIs is 1, right? The only thing, in fact, the rules for this matrix are they're non-negative and the column sums are 1. That's the rules for this detector matrix. It's a randomized, it characterizes a randomized detector. So you'd say it's like column stochastic or something like that, right? The matrix. Okay. Okay. Now, what you could do is just work out the, you can actually just work out the so-called, detector matrix, which actually you get by just doing literally matrix multiplication, right? So if I do the following, if I multiply my matrix here by here's P and here's Q, I get a 2x2 matrix, which is super interesting. And what it's going to tell me, it's called, I don't know, confusion matrix, or lots of names for this, right? But it tells you actually what the probability of your being either right or wrong is as a function of whether it was generated from P or Q, right? And so that's called a confusion matrix, although maybe for 2x2 it's not. But I don't. It's got some. I don't know what it is. Anyway, and so here you would like if this matrix, this detection probability matrix were an identity, that's perfect, right? Because it means that whenever it comes from P, I guess P. Whenever it comes from Q, I guess Q. By the way, would that ever happen? When do you imagine that's possible? Somebody give me an example. Yeah.
When distributions don't overlap?
Yeah, they don't overlap, right? So here's P. I'll draw a P here. It's 0, 0, 0.5, 0.5. And here's Q. This is P, and here's Q. It's going to be 0.3, 0.7, 0, 0. Okay? So they just have non-overlapping support, or they're just different. And so this is silly, but now if I tell you the outcome is 3, what can you say? And with certainty, you can say, if the outcome is 3, it can't have come from Q, so it came from P, right? And if the outcome were 2, it came from Q, not P, right? And so in this case, if you had a reasonable deterministic detector there, you would come up with this detection matrix being the identity, meaning you make no mistakes, right? Right. I mean, that's that's a silly thing, but nevertheless, that's the idea. Okay. So what you really end up having in the choice of T now is this is a multi-criterion problem, right? So because there's two, actually, you can even weirdly say that, this matrix only has 2 free parameters in it, right? The probability of a false negative and probability of a false positive. Both of those you want small, right? So we could say it's a bi-criterion problem, and it would look like this, right? It looks exactly like this. So T, yeah. So this is what you would do. These are your false probability and false negative, false positive, false negative probabilities. You want them both small, right? So what's cool is over here, I mean, with this ridiculous example over here, we could make both of them 0. Right? But in general, obviously, you can't do that, right? So it's a bi-criterion problem, and it looks like this. That is an LP, right? Actually, it's an LP that's so simple, it has an analytical solution, which you could work out. We'll get to that in a minute. But if you scalarize it, and so lambda would be the penalty that tells you how much false negatives bother you more than false positives, right? If you solve this, you actually end up with a solution that is a deterministic detector. Okay, so you get, and as a matter of fact, the method is actually incredibly simple. It's really dumb. It basically says that it depends on the ratio of P over Q, right? And so this is I guess they call it a likelihood ratio test, right? I mean, this is a super dumb example, but actually this kind of works in infinite dimensions and things like that, right? So it'd be the exact same thing in infinite dimensions. If I had 2 continuous densities and I say, hey, here's X, which density did it come from? You look at the two, what you do is you'd look at the ratio of the densities, and then there's a threshold, which you interpret as how much you care about being false negative compared to false positive. And if you're above the threshold, you guess one distribution. If you're below, and all that kind of stuff. Okay, everybody got this? So, okay. Now, those are deterministic detectors. But you could do other stuff. Like you could say, actually, here's what I care about. I want to minimize the probability of being wrong. Minimize the probability. Did I say maximize or whatever? I want to minimize the probability of being wrong, right? And so there you're minimizing the max of these two things. That's an LP, and it usually ends up not being a deterministic detector. So we'll we'll quit today and we'll start up again next time.